Right. And so if x nu is the old, and so I think we should just talk about relativity at a higher level. Why he? So as you said, he came up with tensor. He wanted to have a tensor equation because if those tensor equations are valid in one coordinate system, they are valid in all coordinate systems. And he thought, like in special relativity, one of the postulates is laws should be same in all frames of, like inertial frames of reference. So in general relativity, he extended it to say that it's same in all frames of reference. Even if it's accelerating, that is one of the marks. I think the philosophical ideas that he brought in. It wasn't just equations. I think that's the difference between how they are doing string theory. I feel that's the difference. How they are doing string theory right now is more, I don't know enough, but from what I have seen, it's more mathematical. Like they are doing maths and let it tell them something. Versus here, where he had these ideas, concepts, and he used maths to just describe them.
Yes, exactly. Yeah.
So, so that is one, and that's because of he thought all equations, the laws of nature should be same in all frames of reference. So tensor equations, because they can transform between different coordinate systems. That is one thing, and the thing is why he thought. I was looking at Riemann and his geometry, and at one point Riemann was saying that maybe gravity is because of space curvature.
Yeah, he had that idea.
But and people debate that if Einstein wasn't around, someone else would have come up with general relativity and all. But I feel that first of all, Riemann would not have given a complete picture because of space-time and all. He would have just looked at space, and it would have turned out wrong. But even if Einstein was not around, I think no one would have looked at it geometrically. I don't think so. That's what I feel.
I think eventually.
But I mean,
not.
I don't know
if
anyone who was looking at gravitation geometry. Like right now, knowing all that we know, like I imagine, like if Einstein was not there, Lorentz and all those guys would have like went in that direction, tried to like how we are doing right now. I think, like for example, dark matter. Or some other thing that we can't explain, we try to fudge around the equations instead of looking at it.
Yeah, this is a very interesting question because dark matter, so the majority opinion is dark matter, dark energy, but not everybody believes that. Some people were you the one who posted this?
Yeah.
There are some alternate theories. I actually got a book at the library. There's a book by one of those guys. It's a popular book, kind of like talking about his theory, which is just an enhancement to general relativity. Of course, he doesn't tell you the math, and if he did, I might not understand it. But there's serious people who have, say, forget dark matter, dark energy. What we really need is an enhanced theory of gravity to explain this anomaly.
Yeah.
They're in the minority, but they're serious people. They're not kooks or anything.
Yeah, no, but I'm saying like the top scientists, like the major players at that point, like Lorentz and all, they were really well known. They were pushing for this ether and all those things. Like right now, so like what I saw, that those guys, they really question, like they came up with gravitational theory in 1915, Einstein, then Kaluza came up with unified theory in 1970. Like they were really, and they were looking at the philosophical implications as well. I think like what does quantum mechanics mean? They were arguing about that.
Yeah.
Right now I feel like they don't argue, they just say like maybe because they knew each other, they were. Right now it's like Einstein is God for someone, like he was a great guy and let's just keep on talking about what he did. But I'm saying like Einstein came up with special relativity, which itself, I don't know if people would have come up with that thing if he was not around, like they would have struggled maybe eventually.
Not so soon,
But the difference I feel is maybe even if they come up with it, it won't be like the clarity that he came up with. Like that was very important, like the clear picture, like this is what is happening, time simultaneous. That was very important. For example, if we consider like string theory, there are many people who are going in different directions, not really.
Yeah, there's no
clear picture what's happening.
So
it's just, I think the same thing would have happened to gravity. Even if people had started geometrical, and people had started but I think they all started because of Einstein. That's what I think. One guy was saying that Hilbert came up with the equations before Einstein. He came up, but Hilbert attended a lecture from Einstein.
Yeah. See, he was just good at doing the math.
Exactly.
So he came up with the right equations first, but he never claimed anything because he knew perfectly well. He came up with the equations, but he didn't have the idea. Yeah.
I mean, he attended Einstein lecture. Einstein told him that I have a mathematical problem. He just solved it. Like Einstein also solved it eventually, but they almost solved it at the same time. Then there are other guys who were I think they looked at Einstein because he was lecturing around like I'm working on this theory. So, but even then they came up with a wrong picture. So first of all, the idea that it's a geometry itself would have, I don't know if he would have, if he would not have proposed it, if anyone would have thought so clearly about it, like the principle of equivalence and all. Maybe they would have come up with like this. For example, the difference between Einstein and Newton, I feel, is that like he came up with that GMM R square. Most of the theories I feel is equations, like electromagnetic is like these are the 4 equations, but there is no underlying thought process. What's like we just are doing pattern matching, like we see this is happening. Let's explain it some equations, but there is no underlying like because of philosophical approach. Like, that's why he liked Mark and all. I think. Maybe. But and then I think from what I saw till now, that has guided. Like he used that Riemann geometry. Basically, he tried to geometrize gravity and the other forces. And if you see, quantum mechanics is a different approach. But if you see the string theory and all, the maths they use is similar. Like they use this Riemannian maths for higher dimensions. They try to geometrize things in quantum gravity as well. I mean, obviously, it's geometry in quantum gravity. So because geometry was so useful to him, or it turned out to be so correct in gravity, he thought that maybe he can use it to describe electromagnetism. All the so he knew perfectly well that equation is not the right. I mean, not the like he needs to work more because that equation gives geometry and energy momentum tensor on the right hand side, but it doesn't explain why energy, what is mass, what is energy. So he wanted to explain it, that mass, energy, everything geometrically. And he thought that from that quantization will automatically come up somehow. So he never introduced quantization in his higher dimension theories. Right now in quantum gravity string theory they introduce quantization, they force quantization in. But so because of that I don't think it won't be a theory of everything maybe, because you will have to explain why are you like quantization, why is it coming about. Like maybe you can come with like the difference between a good theory maybe is you can come with a formula like this is how it works versus like GMM by R square versus this is how it really like there's a curvature and the geometry is changing. I feel there's a difference why it's happening. Like he hasn't explained why C is constant. Like C is constant.
That's
so that no one is trying to explain.
I know, that seems like that's such a big clue to something. I don't know what. What is that? What is that? What is really going on there? It's something very basic about reality.
But we need to slowly. But I think they are relying on maths a lot. I don't know, but from what I see. But we have to slowly learn the maths and see what they are doing to figure out if it makes sense to us. Okay, so let's go back to maths. So if x nu is a old coordinate system and y nu is a new coordinate system, then any function linking x nu and y nu are permissible as long as those functions are differentiable. Each point in space-time is uniquely labeled. Each point in space-time is uniquely labeled. We move freely between different coordinate systems using transformation properties. And those transformation properties will involve partial derivatives of the coordinate functions of contravariant vectors and all those things. So we should be able to move between these two, basically. So now contravariant basis vectors. Tangent to the coordinate curves along which only one of the coordinate changes. So those are contravariant basis vectors. I think basis vectors is I think basis is like xi. This is the basis vector. Like x, y, z, like ex. Is the basis which is constant here, but there are coordinate systems where those change as well. So those are a function of x. one form basis vector gradients of the coordinate surfaces on which only one of the coordinate remains constant. So bases of above sort that change with coordinates are known as coordinate bases. These are bases we will implicitly use from now on. Like this Cartesian coordinates are special forms, but even if you see the polar and all those basis vectors, they change with the coordinate system. However, they are saying that transformation properties of the components of vectors and one forms are transformation properties are basis independent, meaning we usually don't need to worry too much about basis vectors and basis one forms. Crucially, basis independence means if a tensor equation is true in one coordinate system, it will be true in all coordinate systems. So this is important, like transformation properties of the components of. So basically when we transform it's the components. The vector is same, but it will have different components in different coordinate systems.
Right.
And we use transformation properties to transform from one coordinate system to different coordinate system. And those are basis independent. So that's why tensor equations can easily transform from one coordinate system to different coordinate system. And basically different coordinate systems are basically different reference frames if you really look at it in that way. So that's why it's independent of what reference frame you are. A contravariant vector acts linearly on one form to give a scalar. This works because the relation between basis vectors.
Wait, say that again.
A contravariant vector acts linearly on one form and vice versa to give a scalar, a real number.
So when you say the one form, you mean the e's?
No, one form is covariant. A contravariant, contravariant vector, they act linearly on covariant vectors. They are called covariant, right?
Write an equation or something.
Yeah, I was going to write. Like E alpha and E beta to delta alpha beta. Like this is contravariant, this is covariant.
Okay.
Like this is tangent, this is gradient.
Now those are basis vectors.
Yeah.
So the alphas and betas aren't components.
Sorry. This works because this works. The contravariant vector acts on linearly on one form to give scalar. This works because relationship between basis vectors and basis one form is defined using this chronicle delta.
So that there, just to make sure we're on the same page, that's an outer product between two vectors, not a multiplication of components. I mean, E alpha is a whole vector, and E beta is a whole vector, and we're taking the outer product of two vectors to make a matrix.
Yeah.
Okay.
And if you look at the one form, and so this, they represent it by this. This is one form, this is vector.
Okay.
If you multiply this is P alpha, P beta, E alpha, E beta. So which is equal to P alpha, P beta, delta alpha beta. Which is equal to P alpha, V alpha if you say alpha is equal to beta. Which will then come down to P0 plus P for 3 chord for these things what we call dimensions. Will come down to this.
Okay, so yeah, I think I'm okay with that. I found this in this kind of thing. I found the notation to be kind of tricky because sometimes a subscript points to a component, and sometimes the subscript points to an entire vector.
Component.
You know what I'm saying? In other words, right here we're multiplying one component, a scalar, times another scalar, times a vector, times an entire vector, times...
Yeah, but this is P actually. It has a component and a direction. So we just split it so that we can count with this. So this and this is P one form, and this is vector.
Yeah, I agree. I mean, I agree it's correct. It's just I found it, when I was reading this, I found it kind of tricky because sometimes you're really talking about indexing to a whole vector, and sometimes you're talking about indexing to a component. You know what I'm saying?
What is component and what is...
Well, these alpha here is one component of this vector.
Like it will take P0, P1, P2.
Yeah. Well, I mean, yes, but each time, I mean, so.
So no, I think if you expand it, I think it will be easier to maybe understand.
Yeah, so.
E0.
Well, let's make it 1 so we can.
So that will be 0, right?
Yeah, so this will be 0, E1. So here you've got a number times a number times a vector times a vector.
Oh yeah.
So that's what, when I was first reading this, I found it hard to make it work because I wasn't remembering that. These guys, E0 is a whole vector, P0 is just one number, right?
Yeah.
So maybe that was obvious to you, but I found that a little bit tricky. I would have found
But
it easier.
E0 is also a component of a vector, right?
No, that's a whole vector. The E's are not, the E's are vectors.
So E's are these things, the basis vector.
Yeah, so here's E0,
Yeah.
E1.
No, but I'm saying if you take a unity vector, like these are the components E0, E1 of that U. If you take E unity vector, yeah, actually unity.
Well,
Yeah, these are like I, J in Cartesian coordinates. So these are like vectors, but in one direction. It has only one direction.
yeah.
It's in
Well, they're in one direction, but you could, I mean, they're actual vector. This is a very different kind of object than this is. This is just a number, and this is a vector.
Yeah.
So it's
So
a little,
actually, it
it's a
should be
little
like
tricky. It's a
actually
little-
it should be like E0. No, it's like a vector. So for example, a vector V is 2I plus 3J. So you will say that P0 is this 2. It's like magnitude in that direction.
Yeah.
So P0 is a magnitude in E0 direction and V1 is magnitude in E. And then so this is I is E0. This will be P1, E1.
Right. But it's a little tricky because this, it looks like, I mean, this is a different kind of object than this is, but it's not obvious from the notation. And this originally confused me a lot, but it's okay now, but the way they use the subscripts, it's a completely different meaning of the subscript.
I think why it happens is if you look deep enough, is vector is like dx for them.
I mean, occasionally, sometimes I've seen, I don't know if he does it, but in some books I've seen it where they actually need to refer to a component of one of these vectors. And then they have to do something like, something like that. Anyway.
I think that might be like E beta in a different part. Alpha is a reference.
No, I
frame.
think it was a case where the guy he needed to refer to a component of one of those vectors in some.
But I don't think he will have.
some
This won't have a component, right? I mean, yeah. This won't
Well, it'll have a component if you need to look at it in some other basis.
Yeah.
Yeah.
It will have a.
Yeah.
Yeah, you're right. Yeah. It will have a component in this. If E0, like if the matrix is not diagonal, that means that right now it means that they are perpendicular to each other, kind of. Since this will be 0. Like if it's I and J.
Well, those guys, but I mean, those guys might not be. In fact, those guys probably won't be perpendicular.
No, I'm saying right now I'm saying for this, they are. Otherwise, the diagonal elements because it's like 1, 1, 1, 1.
Oh, because we're still in we're in a flat space.
Not just it's flat space and it's Cartesian coordinates.
Yeah.
So, yeah, because this. I mean, it's 1, 1. If there's r square and all, even then it's just diagonal, right? Yeah, it need not be actually.
But
no,
in general, those guys won't be
in flat space. Yeah,
perpendicular.
I'm sorry, not because they're perpendicular, because we are in flat space.
Yeah,
It's
yeah. Okay,
because how the metric works out.
Yeah.
Yeah. So what were we saying? Yeah, this can have a component in the, like if they are not perpendicular, or if I think if they are not Cartesian, then mostly they have some components with respect.
Yeah, they won't be perpendicular. Anyway, so I'm good with this, but it took me a little while to get good with it, to figure out what he was saying.
But I think the basic thing is this vector is like dx, and this one form is like d by dx. So
Yes.
That's why it comes out to be a scale.
Yes.
And then last time we were also discussing why they have just this contravariant, covariant and all. I think using this you can easily transform. There is a deeper, I think, mathematical explanation as well, but
Yeah,
right now you can just say that you can easily transform from one form. The only reason they want these mathematical tools is you can use this to transform between coordinate systems. So now scalars do not change during a coordinate transformation. Like in any coordinates, for example, they have given temperature. If it's in a spherical coordinate, it will be equal to x, y, z. Then contravariant vector. Contravariant vector has upper index. And I was reading the Einstein's original paper, and he says that the upper index convention came from Ricci and Levita, who were those guys, mathematicians.
Huh.
Ricci, Levita, whatever Levi, something the name.
Oh, yeah.
Ricci is a tensor as well later on.
Yeah.
That guy, and there's something Levi.
Oh yeah, CV.
Yeah, CV Levita or something.
Yeah, I know. They have a special symbol too, with three. Like the Kronecker delta, they've got a Levi Civita.
The
little epsilon symbol, I think it is.
we'll have to see.
They've got a special symbol of their own.
That connection thing, this thing, Christoffel symbol. What is Christoffel symbol?
No. They've got a symbol. It's an epsilon.
Oh, I don't know.
Alpha, beta, gamma comes next, and it's a special kind of a. Well, we don't need to go there now. They have a special symbol that has to do with ordering things.
So contravariant vector has upper index and has components that transform under the coordinate transformation. So V M alpha equal to this. So I just expanded it so that like we can look at it in a better way. For one of them I expanded, like if alpha is 1, so this prime is one coordinate system, is Vx prime 1 Vx 0 partial derivative V0 plus dx prime 2 dx.
I think that's still 1.
Yeah, I'm sorry. 1 dx 0 dx.
Yeah, there you go. That's a 1.
V1 is dx prime 1 by dx 2 V2. So this is what happens, like if you go to another coordinate system prime, then the first component will be a function of all three components in that coordinate system, and how the other three coordinates are related to x1, x2, like how x prime, like for example if there is, I think I should draw that. There are two coordinate systems, suppose. This is prime, this is not unprimed, this is 1, 2, 3, 1, 2, 3. Then in this, so we are looking at this prime first, this coordinate, and it's related to all three, v0, v1, v2. Let's see. 1, 2. So we are looking at 1. So it's related to 0, 1, 2, and how this is related to this is related to this.
Right.
Differentiation of with respect to x0, sorry, x prime 1 with respect to x0, x prime 1 with respect to x1 and x2. Like it's just x prime 1 like dependent. And then you have prime 2, then you will see like it's just actually that thing, what is it called in calculus?
Oh, a total derivative or something like that?
Like you have that multiplication product, some product rule there. Like if you have the dy by dz equal to dy by dx by dz, like a basic calculus product rule, we have introduced a dx. Like dy by dz will be dy by dx.
Yeah, it's not a product rule. It's
No, not product.
it's
sorry.
like a chain rule.
Chain rule.
Yeah, there you go. Yeah.
So it is similar. Like if you consider.
Yeah.
Because this v0, like there is a v0 component, and you see how dx1 is changing with respect to
Yeah.
0.
Yeah. I'm totally with you.
Yeah.
I'm with you.
And for one form, it's like d prime alpha dx beta dx prime alpha d beta. So if you expand it, it can be v0 equal to dx0 dx prime 0 v0 plus dx1 dx prime 0 v1 plus dx2 dx prime 0 v2. So basically, 0 v1. So this is also actually a that chain rule sort of thing. V prime 0 dx0 dx prime 0. Yeah. It's also similar.
Yeah.
But I think I don't know. It's easier, I think, if you maybe if you say like this will be a form d by dx0 maybe. No, d by dx. No, this will be a form d by dx0 plus d by dx1. I mean, comma d by dx2. Then you can see that this dx0 will get cancelled here. dx1, dx2. Because the earlier one was like dx. I should have just kept it. But earlier one was like dx.
Right. Yeah, the first one's like dx. The contravariant's like dx.
Yeah. So
And then they would cancel.
yeah, because it has like upon dx0 v0, so that will be dx0.
Yeah.
Upon dx.
Yeah.
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 So this is how. So this is basically one is tangent. One is like tangent of the gradient. Sorry, tangent of like dx sort of thing.
Yeah.
Another is gradient of that function. One is like small distance on that curve. Another is like gradient of that curve. So somehow, so if you multiply them, you get some. I don't know, but not multiply them, but these two things will help you transform. I think that's a basic concept.
I still find it easier to kind of understand, you know, at a gut level what's happening with the contravariant things, and with the one forms, I'm still kind of like I've memorized the equation now, but I still don't quite have a.
So contravariant, what do you think? Like,
Well, I mean, it makes sense to me more. Like I visualize it as you know, I can visualize it as the infinitesimal tangent, you know, there, and the transformations make sense to me. The gradients, I'm still kind of okay.
So I think gradient you can visualize is like what is gradient? It's like d by dx, d by dy, like actually x0, x1, x2. This is gradient and it will have like I, j, like forms.
Yeah.
So these components you are transforming to another, like from this.
Yeah, I mean, I know that. It's just that I guess I think of the gradients as the I could think of them as the level lines. What do you call it? You know, you can think of the gradients as the iso lines. You know what I mean?
So gradient is basically change of the function.
Yeah.
In that direction, like.
But you know, how's that different than the? I mean, the tangent is.
Like if you have a curve, I think a very infinitesimal, like dx.
Yeah.
Will be like a tangent.
So that's the tangent. So what? Draw the gradient.
How do you draw?
Draw the gradient.
Yeah. Gradient, like will be dependent on this curve, I think. So if you differentiate with respect to x, you won't get it on the curve, but you will get a function of how it's changing. It's the slope, I think. It's like it's a d by dx.
But so it's the slope of the tangent. So the tangent's the tangent vector.
No, for example, let's look at a curve. Like, say, I don't know how the curves look like. How will x y equal to x curve look like? Like if this is x, this is y. So y will like, it will something look like this. I don't know if it's a parabola or whatever. But it will like, as x increases, y will increase exponentially, like power 2. Like for this is 4, this is 16 now. So now, I think gradient will be like 2x. So gradient curve will be a line with slope 2, I think. Like some line. That will be the gradient curve. So at each point it like, so no sorry, y could be 2x, so it will be 2 at this point, 4 at this point. Yeah, so it will be like a line.
So that's the gradient curve. So, you know, I can picture how the dx, how the tangent, I can picture kind of like what that transformation means. I have trouble picturing, you know, getting a picture in my head of what the transformation of the gradient really means. I mean, I don't know how important it is to have a picture of that in my head, but...
I think it's important.
Do you have such a picture in your mind? Like,
I think like picture will be difficult, but I think from what I look at, from the way I look at the equations, like the gradient is basically rate of change, like how if there is a function t of x, y, z, how t varies with respect to x, how t varies with y, how t varies with z, and then you want to know how it will vary in the different, like r theta, for example r theta phi, how t will vary with r in a new coordinate system. Like you know how t varies with x, y, z. So x, like what contravariant, I think is a dx, and you would and transform it to a different coordinate system. Even that one, when you so even okay, I think I can explain that. Yeah. So contravariant. Let's look at contravariant first. You know that, but the point is you have two coordinate systems. For example, this and this. For example, x and y. You have a curve here. You have a curve here. Some coordinate system. You have a dy here, dx here. Now the dx won't change because you change coordinate system. The actual length dx square maybe, or dx won't change, but the components will change.
The
right?
components will change, and
So
I can visualize that.
Yeah, you can visualize that, right? Now there is this was a dx, but this is a function.
This is a function.
It's rise on a curve, some functions. For example, consider this as t, some function of x, y, z. Consider for now. Consider this x, y, z. Consider this r, theta, phi. These are not spherical or Cartesian, just a name them something. And now you know this is the length, but this is how the function is. Now this function will change when you change the coordinate system. So you transform the length, but you don't know how the function will change because you know how the components of length look like. But if you want to see how the curve will be in this, it will be different. It won't take the same form because the coordinate systems are different.
Okay,
Because
so in a certain sense, I'm just transposing a curve.
Yeah. So I will show you in equations how it will. So you know how the components of that length will look like, but you don't know how, because if you have the components, but now if you want to calculate something on this curve, you don't know how to, because you don't know how the curve will look like. It's not even related. You can just say that you know the components of dx. Now there is a curve on which dx lies on the curve. Let me see how, because a curve y equal to x square in a different system may not look like. It won't look like.
Okay,
So if you look like, if this is t r theta phi, this will, so there will be an equation. So now if you look at t, it will be like, now I want to know how dt varies with r. I know how it varies here, but I don't know how it varies here. So dt by dr will be dt by dx, which you know, into dx